Okay. Is there anyone who has a USB-C cable? USB-C to USB-C cable? Some US? No? Okay. So because of the fact that I have I essentially forgot to bring my other USB-C cable, I cannot connect my laptop to the charger, so I'll be streaming on YouTube. It doesn't concern any of you, but it is important for the online experience. Sorry. Okay, the last thing we talked about on Wednesday was the stream functions, right? Yes. Yeah, thank you. Appreciate it. Thank you. Thanks a lot. Thank you. I don't know. I mean, I guess. Just pull it. It's a little. Okay, got it. Yeah, got it. Thank you. I appreciate it. Yep. Okay. I guess I have to get one of these. So let me just share my camera with the YouTube, with the Blackboard. Okay, the last thing we talked about on Wednesday was the stream functions. I guess so. Yeah. Right? That was the last topic we covered on the stream function, and we are going to move forward from there. One quick announcement though, your homework 2 is going to be posted on Wednesday, and it will be due 1 week afterwards. There won't be any class on Monday because it is, what do they call it? Like resting day, whatever they call it. They have wellness day, yeah, wellness day. It is a wellness day, and we don't have any spring break this semester because they didn't want any of you guys to go home and spread the germs, I guess. And so we don't have any class on Monday, but what I'm gonna do for Monday is I'm gonna upload a tutorial on how to use ANSYS Fluent software for graduate student projects. Okay, so if you want to do that project, it will be uploaded on YouTube. So I will share a link in both courses, both sections of the course. So anyone who is interested can have access to that tutorial. But there will be, there are millions of other tutorials available as well. So you don't have to watch this one if you want to learn about ANSYS Fluent and how to simulate something in simulate an aerodynamic related problem in ANSYS Fluent. If there is no question, let's continue the discussion. Today we are planning to finish chapter 2, and we will solve some example problems, hopefully on Wednesday. Then we'll start chapter 3. So we stopped at stream functions. The next topic we want to cover is the angular velocity. But before talking about angular velocity and introducing the formulations and the formulas we have to use to calculate the angular velocity of a fluid, we first have to understand the different types of motion an element of fluid can go through. So let's say we have this very small element of fluid. It is moving on this streamline. It can translate to this location. So this is one type of motion a fluid element can go through. Translation. No. While it's translated to that location, it can rotate around an axis. So rotation. And it can also be distorted, meaning that the distance between these points can become larger or smaller. And I already have a distorted cube there, so I'm not gonna distortion. So three types of motion: translation, rotation, and distortion. And a fluid movement in general is a combination of three. Some of them can be present in some form, and some types of fluid movement, and some of them can be present in other types of fluid movement. I assume you have seen the translation of a fluid extensively in your fluid mechanics, and some rotations, but you have not talked about distortion of a fluid element that much in your fluid mechanics. We are going to talk about mainly the rotation and distortion parts today, and we will see that their importance in aerodynamics. So let's talk about them. When a fluid element is rotating, or there is some sort of a distortion, this is what can happen to the fluid element. Let's say it is also translating, and this is the original position you would expect for the fluid moment. What's going to happen when it distorts is that these points can move this way, and we can have the movement different points can move to different locations. So this will be how your new fluid element would look like. The point is, these angles are changing, right? We're gonna have new angles. These angles theta's. Based on the movements of these from your solids, you can see that we can calculate the strain and the angular strain and the angular velocity, which is going to be a concept we are going to mostly be focused on in fluid mechanics. But how do we calculate the angular velocity? Are we clear? So the angles are changing, we will have angular velocity. That's the idea. But how do we calculate this angular velocity? The derivation of this is actually in your book, and it's also in the notes. But we are not going to go over the derivations. I'm going to give you the derivation as a bonus point, which I usually do. So I want you to derive this equation for angular velocity for me. So the general formula for angular velocity in 3 dimensions is going to be looking like this. Partial u partial z minus partial w partial y. And just as a reminder, the velocity vector has 3 components, and we are doing the Cartesian coordinate system. So UV, right? Plus, this is actually partial v, plus partial u partial z minus partial W partial X J, right? Yeah, plus partial V partial X to the small v partial U partial Y K. So the bonus point is going to ask you to, I want you to derive this. Let's start from here, the changes in these angles, and then get to the final derivation of the angular velocity. So angular velocity omega, we can calculate it using this equation. What does this equation remind you of? This format of equation, what does this remind you of? If you look closely, this equation is actually 1/2 of curl of the velocity vector. So angular velocity is going to be equal to 1/2 of curl of velocity vector. But something that is going to show up again and again in your calculation is a new parameter, epsilon, which is 2 times the angular velocity. So it is just the curl of your velocity. This new parameter is called vorticity. Have you seen for vorticity before? Okay. So it's just twice the angular velocity. And this is going to be a very important parameter in aerodynamics and in fluid mechanics in general, but especially in aerodynamics. So this is going to actually help us come up with the new classification of the flow when it comes to rotationality of the fluid flow. Or when the curl velocity is 0, what we are going to do is we are going to say that the flow is irrotational. When the curl velocity is non-zero, is a finite parameter, finite number, then the flow is going to be rotational. So a new classification is going to emerge from the definition of vorticity is irrotational and rotational flow. 2 types of flow, whether the flow is rotational or irrotational. But actually eventually end up pointing to the fact that your flow is going to have vortices or not. If your flow is irrotational, then you won't see the presence of vortices in your flow eventually, which is, we will talk about it in more detail later. Is there any questions so far? So this is chapter 2 is in general is mostly definitions. We are going to learn some new tools and be reminded of some old tools to use in chapter 3, chapter 4, 5, and 6. Okay. So we talked about angular velocity, but the other point that I briefly mentioned was a strain. How can we calculate the strain of a fluid element? We are already familiar with the concept of a strain, what it is and what it means when it comes to solid. It essentially has the same representation in fluid. We can calculate the strain for each plane as epsilon of. So one thing that I think I need to mention, we call both of these epsilon. So this is epsilon, and this is also, that's what I've heard here in this country. epsilon, but this is actually the Greek letter Kisi. So not epsilon. It is worth mentioning. This is the real epsilon. But make sure not to confuse vorticity and epsilon and a strain. Okay, so a strain in the xy plane is going to be equal to partial v over partial x plus partial u over partial y. A strain in the xz plane is going to be equal to partial w over partial x plus partial u over partial z, and a strain in the yz plane is going to be partial v partial z plus partial w partial y. Any questions so far? So what will happen to our formulation and definitions, especially when it comes to vorticity? What will happen to it if the flow is two-dimensional? This is mostly the case in this course, at least. We will only have 2 chapters that deals with three-dimensional flow. So what will happen to that equation, Kerr-law velocity, or the equation for vorticity, when the flow is two-dimensional? I assume all of you, or most of you, have the equation in your notes. So what will be the equation for a two-dimensional flow? The first thing you need to do is to cancel out the terms that have W in them, right? And the changes in the Z direction. That's the idea of a two-dimensional flow. There is no velocity in the Z direction or in the third direction. So based on this, what will be the vorticity equation in 2 dimensions? Anyone? Okay, it is not that hard to figure out, right? You have to find a determinant of this vector, Cartesian coordinate system, u, v, w. This goes away. This also goes away. How do we calculate this determinant? This is this multiplied by the determinant of this a smaller one, which is going to be 0. This multiplied by the determinant of this one, which is going to be 0. So the only one term remains. So we are going to get partial v partial x minus partial u partial y k. So this is vorticity equation in 2 dimensions. Okay, so if the flow is irrotational, then that equation has to be equal to 0, and partial v partial x has to be equal to partial u partial y. Okay? Any questions so far? We can combine all of this analysis in actually one big matrix of the gradients. Okay? A 3x3 matrix. On one side, we are going to get the partial x, partial y, and partial z. The other side, we're going to get u, v, w, which essentially means that we are going to get partial u, partial x, partial v, partial x, partial w, partial x, partial u, partial y, partial v, partial y, and partial w, partial y, partial u, partial z, partial v, partial z, partial w, partial z. Okay, we can combine everything I've seen as far as the strength and the vorticity in this matrix. What can you say about these terms, these diagonal terms? What is the significance of these terms? Unidirectional. Okay, that's a good point. So what does it signify? Go back to the equation. Yes. Exactly. So these three terms are talking about the expansion or contraction in each direction, right? And if you add all of them up together, you're gonna get, and if you add them up and you get 0, you're dealing with incompressible flows. It means that whatever expansion you have had in one direction was compensated by contraction in another direction. Okay, so these are essentially dealing with dilation of the flow. So these diagonal terms signify the dilation of the flow. These other terms are mainly focused on the rotation and a strain. A strain. Okay, so for a flow to have some sort of a rotation or distortion, at least one element on this matrix has to be non-zero, right? That's the idea. Any questions here? Let's go back to the irrotational flow definition for a second, or rotational flow definition. Pardon me? We are dealing with these definitions? No, these are just definitions that can apply to any type of flow. Because we didn't assume the flow is like the density. We didn't make any assumptions. It's just a mathematical analysis. Okay, so let's go back to the definition of irrotational flow. The idea was the curl of velocity has to be 0. So this value, or essentially vorticity, has to be equal to 0. Okay. If we go back to the definitions we had, if you recall, we had the gradient of a scalar is always a vector. And here we want to define a scalar which gradient is going to be velocity. Okay, so this value is a scalar, whatever that is. We want to find a scalar which is going to be, when you take the gradient of it, it will give you the velocity. Is this clear? So a scalar which is going to give you the velocity when you take its gradient. Okay. Why is this helpful, or why is this, like, mathematically or physically? Why can this be helpful to us? Go back to the definitions of a stream function we had. The idea was, if we can find this function y, we should be able to find the velocity in each direction by just taking derivative. So it's going to be very helpful to us. If you know the string function for a specific type of flow, you will always be able to find the velocity in any direction, right? This is essentially going to be the same idea, because as long as you have as long as you have this velocity potential, you will be able, this scalar value, you will be able to find the velocity vector. And we're going to see how we can do that. First of all, this phi is called velocity potential. And then if you have the velocity potential for a specific type of flow, you will be able to find the different components of this potential, mainly because, I'm going to show this to you. In Cartesian coordinate system, these are what the potentials look like. So why is this the case? Because the gradient of this scalar, like random scalar value, which we have called this velocity potential, is going to be like phi I plus the gradient partial x partial y j plus partial phi partial z k, right? And the velocity itself has three components: ui, vj, and wk. So if you have this potential, this velocity potential value, you essentially, by just taking the derivative, you will be able to find the velocity in each direction. Any questions so far? So two of the most interesting tools we have learned about so far is the stream functions and the velocity potentials that are going to give us the velocity vector. And when you have the velocity field, you essentially have a lot of information that you're going to need to be able to analyze and find aerodynamic forces, right? And we're going to see that later on. Just today, we're going to see that in a couple of minutes. I'm just going to give you the formula for velocity potential in other direction, in other coordinate systems. Then we'll try to compare this velocity potential and the stream function. So if you are dealing with Cartesian coordinate system, you just have to take the derivative with respect to x, y, and z. It will give you the different coordinates of the velocity potential. But what if you are dealing with the cylindrical coordinate system? For VR, you just have to take the derivative with respect to r. For v theta, it's going to be 1r partial phi partial theta. And for vz, is going to be partial phi partial z. Okay. For this spherical coordinate system, partial phi partial r, v theta is going to be 1r partial phi partial theta. And then one of the axes of the spherical coordinate system is called phi by itself. So v of phi is going to be 1 over r sine of theta partial phi partial phi, essentially. Okay, so we have this formula. If you have the velocity potential, you should be able to find the velocity in any direction. Okay. But what is the difference between this velocity potential and the stream function?
I have a good question. Is that v theta for this one, coordinates, is that d phi over d theta?
Yes, d phi over d theta.
On the left side as well?
On the left side?
Yeah, first v theta.
This one? V theta?
To the left of that one.
To the left,
Yeah,
this one?
Yep.
That's I'm sorry, d theta over d phi.
Okay.
A lot of Greek letters. Yeah. Okay, so let's go back. Hopefully you have your notes from the previous lecture. Let's go back to your notes from your previous lecture. What were the formulas we had for the stream function? The idea is the stream function and velocity potential essentially do the same thing, right? They give you a tool that will help you find the velocity field. That is the idea, right? But what is the difference? What was the formulas we had for velocity potential for V and U? Is there anyone who wants to jump in here? Let me just, for whatever reason, my camera froze. I'm sorry, guys. Give me 1 second. For the students who are online, you can go back to Blackboard. You're going to see my regular laptop's whatever that webcam that is going to record for you. And I'm sorry, technical difficult. Okay, where were we? Stream functions versus velocity potential. If you go back to the stream function formulas you have had, hopefully you have in your notes, you will see that we only have U and V and VR and V theta. We don't have the third dimension. But that came from the definition of the stream function. Like all of the definitions, all of the tools we use to come up with the stream function formulas was based on. But the assumption we are making to be able to find this del phi is that the flow is rotational. If the flow is rotational, then there will, of course, exist a function that this will be true for, and based on this, able to find the velocity potential. Okay. In your case, you will never be asked to find the velocity potential, but this has to be true, right? So velocity potential has to be irrotational. The stream function, the flow has to be two-dimensional. That's the main difference between the two. And the slope of the line for the stream function is actually 1 over slope of the line. This is dy dx, slope of the line for the velocity potential. Okay. If there's no question, we can move on and talk about circulation. Circulation, a very fundamental and important topic in aerodynamics. A very fundamental and important definition. And it was, the idea of the circulation was developed, I can say, by 3 different guys at 3 different locations at the same time. So it was developed by this guy, I forgot the British guy's name, but the other guy's name is Kuta, who is a German physicist and engineer, and there's a Russian guy who was involved as well, Jakovsky. You'll hear these two names later in the course. These are very important people in aerodynamics, but the first guy, I don't remember his name. So yeah, they came up with this definition for something called the circulation. Circulation is going to be negative line integral of V ds. So what we are doing, let's say you have this object, you have the flow passing over it. We are taking the integral of velocity field over this curve, S, ds. Okay? So ds itself is a vector, so it can be dxi, dyj, dzk, and velocity we already know that it is a vector. Taking a line integral is always, most of the time, is very cumbersome and hard. So it is not a bad idea to convert this line integral to a double integral, or a surface integral. We can use the mathematical theories that I'm going to mention in a second to transform this line integral to a double integral over the surface of this object. Yes, right. That's a negative sign. Okay. Circulation. Let me write the name. It is a very important topic. You will definitely get a question from this, like to find the circulation around an object in your exam. That's like 100% this will happen because it is a very important topic in aerodynamics. Well, how can we transfer? How did we make this transformation? What was the theory behind making this transformation? And it's actually called is there anyone who remembers this from their mathematics? I'm like 95% sure you have seen it in your mathematics. This transformation from a line integral to a double integral using the curl of the velocity. I'm trying to find this in my notes. Anyone? No? You haven't seen this before? Divergence theorem is actually called the Stokes theorem, right? Because it deals with the curl of velocity. But we have another transformation called the divergence theorem. We have actually three transformation. A Stokes theorem, because it was developed by some guy named Stokes. Divergence theorem, because it goes back to the divergence. So using the divergence theorem, we can transform a double integral, the surface integral of whatever vector you are dealing with, to a volume integral. And I'm hoping you are familiar with the volume integral and the surface integral and all of those things, those nice things. And there's another theorem called the gradient theorem that deals with the transformation with a scalar phenomenon for a line integral of something like pressure, a scalar, ds is going to be equals to the double integral of gradient of p dA. Your book uses for curve uses ds, for area also uses ds. So make sure not to be confused. if you are reading the book. So using the Stokes theorem, we can actually transform this line integral to a double integral. We will definitely solve some examples of circulation, but we need to talk about circulation itself. And I want you to answer this question. What do you think the circulation is? What does it signify? It has a name, of course. I assume you can guess something from its name. Circulation, the line integral of velocity, the negative of the line integral of velocity over your object, over this curve, closed curve. So what do you think it signifies? What? Turbulence. Who said that? Yeah. My depth perception is not okay. Turbulence. How would you connect it to turbulence? So you're essentially thinking about the circulations or vortices you're going to see, or eddies, or whatever you want to call them, in the turbulent flow, which is, of course, something that you can get to from the naming, right? It names circulation. It must be talking about flow circulating around the object, right? But this is not true. I don't know why these three guys named this phenomenon circulation, but circulation doesn't talk about the fact that the flow is going to circulate around your object, right? I just want to make sure that you are clear on this, right? Because think about it this way. If you have an object and your flow is circulating around it, it doesn't resemble any type of flight, right? It doesn't resemble any type of movement in a forward or backward direction, right? Which is our flight is. So circulation does not talk about this type of phenomena, flow circulating around an object. But what does it signify? It talks about the fact that if the circulation is finite, as not zero, then you will be able to produce aerodynamic forces. That's the idea. That's it. So it has to be finite for the aerodynamic analysis to go ahead. That's it. That's the only thing. So don't be confused by the naming. If you saw an example problem, it doesn't really mean that the flow is circulating around, right? Just I don't know why they named it circulation, but they have named it circulation. Any questions so far? No. So we can have two different paths moving forward. I want to talk about computational fluid dynamics as well, a little bit. We can either do the computational fluid dynamics today and then leave solving the examples for the next lecture altogether, or we can solve the example today and leave the computational fluid dynamics part of the class for the next lecture. But it really depends on you all. What do you want us to do? Solve an example or continuing the lecture to computational fluid dynamics? Example. We have one example. Two examples. Yeah, that's example. So, okay, let's go for example. Yeah. Okay, so this is a book example, actually. And we want to determine whether a two-dimensional flow is irrotational or not. Let me clean up the board. Okay. So you want to tell me whether a flow is irrotational or rotational. What should we do? We have to take the scalar velocity. If it was 0, then the flow is irrotational. If it wasn't, then the flow is rotational, right? But what is the flow? Boundary layers a little bit, but hopefully you remember boundary layer exists because of the viscous effects near the wall, right? We have the velocity distribution. The x component of velocity distribution is u over v infinity. And this is boundary layer thickness. This thickness is a function of local Reynolds number. So your delta is going to be equal to 5 over a square root of Reynolds number at each point, which is equals to 5 over a square root of rho infinity, v infinity x over mu infinity. And x is the distance from the leading edge. So boundary layer flow is a two-dimensional flow. That's the first assumption. And we are also assuming that the flow is incompressible. So we can simplify the scalar velocity equation as partial v partial x, or partial u doesn't really matter, partial u partial y minus partial v partial x has to be equal to 0. Okay, but here we only can calculate partial u partial y. What is partial u partial y? This is formula for u. Essentially partial u partial y is going to be equal to partial y of v infinity y over delta to the power 0.25. What is this derivative? Final solution to this derivative, I'm going to write it on here, is going to be equal to v infinity over delta to the power 0.25. Delta is not a function of y, so we don't really include that in the derivation. Y to the power negative 75 over 25, or over 4. 25 isn't there. 20 multiplied by 20, 0.25. Is this clear? So what should we do about this part? Partial v partial x. I'm going to give you 2 or 3 minutes to think about it, and then I'm going to expect answers. So we have one of the derivatives that's ready. The other one, we don't know how to deal with. Look at the information we have. So we have, it's two-dimensional, and the other one is telling us it is incompressible. So partial u partial x, that was the continuity equation for a two-dimensional incompressible flow. So we also have this equation, right? So if we can take the derivative of u with respect to x, and we only have that function, we know that delta is a function of x, right? So you should be able to take the derivative of u with respect to x. You will be able to find the derivative of v with respect to y. Does this make sense? Okay, so let's do that. Yeah. Are we confused or are we following?
Was that equation given to you, the u over v infinity equals?
Yes, that was a given. Yeah.
Okay. I'm just confused where the x is, or do we just take that with the, do we derive
The
that?
distance from the leading edge. What do you mean by that?
I'm a little confused, to be honest.
Where's the confusion?
That's the thing, I don't know where it is. I'm just overall confused.
About the whole lecture or this part?
Just this part.
Okay.
Also some of the lecture.
Okay. Okay, that's good, but of course you have to ask questions, right? I don't know how to address your confusion if I don't know where that is. But let's go to the example again. The idea is we have a flow. In this case, it's a flow inside a body layer, right? We have talked about body layers, right? We have introduced the body layers. We know what the concept of body layers are. And we have the velocity distribution inside that body layer. This is given to us, right? And we also know that it's a two-dimensional flow because it's a body layer flow. It is compressible. And the thickness of that body layer is also given to us. So at each point, x, you can find the thickness of that body layer. Outside of this body layer, velocity is going to be u infinity. So this equation won't apply. Okay? Just a regular uniform flow. So for a flow to be irrotational, for a flow to be irrotational, the scalar velocity has to be zero, right? That was the definition. Okay. So if you go back to your notes, we saw that the scalar velocity reduces to this equation for irrotational flow. So if this equation is zero, then okay. So what should we do? We just have to take derivatives, right? We have the functions. Just have to plug them in and take the derivatives. The first derivative is going to be easy. Partial u partial y. This u is a function of y, right? That's the component of velocity in the x direction. We already know that it is a function of y. It is also a hidden function of x because this delta is a function of x, right? That is present here. But in this derivative, I'm taking this derivative, right? So we already know how to take this derivative. So we have this value. Then the next is that we have to find the derivative of v, the component of velocity in the y direction with respect to x. Does it depend on x? You may be confused on how the velocity in y direction can be dependent on x. That's actually pretty simple. This essentially means that the velocity v in this direction can be 2 at this location with the same y, but a different x can be 5, right? So v can be, I don't know, like 1x plus 2x squared, which means that as you move forward, as you progress in the x direction, your velocity in this direction is going to be different. Think of having jets like every 5 meters with different intensities. Yes. What is the delta? This one, right? It is the thickness of this boundary layer. The idea is inside the boundary layer, you have this distribution for your velocity. Outside of it, you will have u infinity. And we are not interested in the outside of that boundary layer. Okay, is this clear now? Where's the confusion? Up until this point. A lot of information, yeah. Okay. Yeah, a lot of mathematics. Now I understand. It can be overwhelming, especially at this time of night. So
for dx, all you have to do is just plug in the values for delta that you gave us, 5 over the Reynolds number, and then that's the function of x that we take the derivative of.
no, we don't have the function of, we don't have v. That's the problem, right? We have u. So you should be able to take partial u partial x, which is present here, right? But partial v partial x, we don't have any information on it. That's the beauty of this problem. You have a question? Yeah. Okay. Okay, you're getting somewhere there. So I just want to be, before moving forward, thank you. Before moving forward, I just want to make sure that up until this point, it is clear what we have done. We have, it doesn't really matter if it's a boundary layer, what is it, right? We have a velocity distribution, we have an equation, right? We wanna find out whether this distribution of velocity is going to be an irrotational flow or rotational. That's it. It doesn't really matter if it's inside the boundary layer, where that is, it doesn't really matter, right? And the idea is this is your equation, and we have this term delta, doesn't really matter what it is, but it is a function of x. A distribution for velocity which has dependencies on y and x. That's it, in the x direction. Okay. So are we clear up until this point? We have just taken the derivative of velocity with respect to y. Yes, you have one question. That's correct. We're gonna get there. So that's the next step. I just want to make sure we are clear until this point. Partial u, partial y is going to give us this. Yes? Clear? Where's the question? Just too much information. That's all right. Okay, so let's move forward. And if you have any question, you can, of course, send an email to me. We can talk about it later. We are going to solve a lot more examples on this. And yeah, so let's move forward. The idea, we were able to find velocity, the derivative of u with respect to y. The next step is to find the derivative of v with respect to x. The other piece of information we have is that this flow is incompressible. A two-dimensional incompressible flow, the continuity equation is going to look like this. So derivative of u with respect to x plus derivative of v with respect to y is going to be 0. We have u, we should be able to find the derivative of u with respect to x. So derivative of u with respect to x is going to be the derivative of that equation over there, which is v infinity multiplied by y over delta to the power 25. Okay, so we are going to have partial x. We can take We can take v infinity and y outside of this differential because we are taking a differential with respect to x. So v infinity y to the power 25 partial x of, or let me actually bring delta to the power negative 0.25. Okay. But this delta itself is a function of x. So it is going to give us v infinity y to the power 25 multiplied by negative 0.25 delta to the power negative 1.25 d delta dx. Okay. The next step is to find d delta dx. D delta dx is going to be, this is your function. So we are going to have a bunch of constants multiplied by x to the power negative half, right? We're going to have 5 over a square root of rho infinity, v infinity over mu to the power, that's d of d dx of this function. You take the derivative, it is going to be half of 5 square root of rho infinity v infinity divided by mu infinity x negative 1.5. This mathematical operation, I don't want to say it's a complex derivative, but it's a confusing derivative. Okay? It is confusing, right? Yes. This is 5. This is just a number 5, right? We could have plugged it in and take the derivative here. That would have been all right. Is that your question? Just, I guess, make it easier for myself. It really depends how. It really doesn't matter. So you can essentially, yeah, you can do that. What was your name? Trevon? Josh. We had one. Why did I type? You are Trevon. Okay. I'm learning your name. Trevon, Josh, Jacob. Okay. Yeah. So what we could do was just to plug in this function here inside the equation, the main equation, and take the derivative here. That would have been correct. Are we all following what is happening here? Yes, we have 1, 2, 3 yeses, 4, 5. So. Okay. That makes sense. That makes sense. But if you have any major questions, let me know, okay? And we're gonna solve more examples. Yes.
This is still dudx, right?
This is still du dx, yeah. So we found that du dx is going to be this long formula. But the good thing about it is that all of these are just constant. V infinity 5, whatever. So whatever we have, we're only going to have y to the power 0.25 as an independent variable, and x to the power negative 1.5 multiplied by 1.25, right? You have to plug this. This is delta, right? This is. We have to plug that in and do the multiplications. Let me go back to my notes and give you the final value for this, because this is getting okay. So let me just put this here. Whatever we have is going to be only constant. Then we are going to get a negative value constant, negative of c, this is a c, y to the power 1/4 I have, or 0.25, let's do 0.25, x to the power negative 9/8. Okay, pretty sure if you plug the values in and do the derivation, you'll get to this part, which is going to be equal, based on this continuity equation, is going to be equal to negative partial v partial y. Okay, okay, so what is the final goal here? The final goal is to find partial v partial x. So we have to take the integral of this with respect to y to find the equation for v. Partial v partial y is equals to cy, and then we have to take the integral with respect to y. What will be the solution to this integral? Yeah.
Y to the 1.25 divided by 1.25 plus c.
That's it. And we are going to have the rest of it. So we are going to like include everything in a C1, y to the 1.25, x to the negative 9/8 plus a C2. Okay. It is very easy to determine. So at the wall, v is 0. That was the idea. Adjacent to the wall, your velocity during a no slip condition is going to be 0, which means that your c is going to be c2 is going to be 0. So v is going to be c1 y x to the negative. So we have partial v partial x is going to be equal to 9 plus 8 is 17, right? So it's going to be another, like, let's call it 3 y to the 1.25 x to the power negative 17/8. Okay, so this is going to be your partial u partial y. This is going to be your, this is actually partial v partial x. Partial v partial x. And we have to subtract these two. Is the solution to subtraction, this subtraction, is it going to be 0? Always 0. Is it going to be always 0? No, right? It may be 0 at some point, but it's not going to be always 0. So this flow is rotational. See? Easy. Rotational. Which is going to bring us to the last thing we want to talk about for just a couple of seconds, and then you will be free to go. Sorry. Do you want me to write them back? Okay. I don't need to wipe the rest of it. I just want to. So let's say this is a fluid element. A streamline, moving on a streamline. The idea was when you are in a viscous fluid flow, so the viscosity effects are not negligible. Okay. Between the layers, each layer of a fluid, there will be shear stress. Okay. And that shear stress, this is something you have seen in your fluids, is a function of your viscosity, the gradient of velocity in the x direction with respect to y. This is something we saw in this course, and you have seen it in fluids. And actually, I'm teaching it in fluid right now. So yeah, so this shear exists, right? And this shear between two layers, right? So this layer is pulling on this other layer, this bottom layer. The bottom layer of this fluid element is applying this shear, or we can like look at it the other way around, to the layer adjacent to it. We will have the same thing. This top layer is applying this shear to the top layer of this element. So the top layer is actually applying the shear in the other direction to it. So we are going to have this type of force balance on the fluid element.
Which way is the flow going? To the left or to the right?
Doesn't matter as long as they are opposite in the opposite direction. The point is that these shears are in the opposite direction, right? So what does it mean? We are going to have rotation, right? So when you're dealing with the viscous flow, your flow is going to be rotational. That's the conclusion from this very confusing example. I actually didn't want to solve this example, but I was looking at it today, and I saw this can be a very good candidate for an exam problem. So it is not a bad idea.
Good thing we went over it.
Huh?
It's a good thing we went over it.
That was the idea. I wanted to go over it to make sure that you are familiar with this type of problem. Okay, is there any questions? Hopefully, if you so the discussions, the introductions of chapter 2 are done. The only thing that we need to talk about is going to be computational fluid dynamics, CFD, which is still a mathematical analysis. So we are not going to write any programs or anything. But is there anyone who is not familiar with MATLAB? Not at all. Okay. Is any programming language, like mathematical calculations? None. I will give you one like MATLAB programming in your homework. I will probably just go like post a lecture going over what you need to know for that programming. But the assumption here at this point is that you have passed the introduction to numerical methods, right? So you should be familiar with basic MATLAB programming. And but we will definitely go over the introduction, okay? If there's no other questions, then that's it for today's class. Make sure to go over this example and the material, because we talked about mathematics can be boring, especially at this time of night. It is boring for me, it is going to be boring for you, but the material we talked about today is important in our discussion. It's going to show up later, especially the circulation part is going to show up later in our discussion. So
circulation is just like a mathematical concept. It's
that's
not
it.
like describing the flow at all. Like it's not the circulation, it's just the mathematics of it. It's called circulation.
That's it. That's it.
Okay.
It is actually it is. I don't want to confuse you. Yeah, that's it.
I'll look into it more.
Yeah.
It's basically what we were doing. So we're keeping that box right there and then like integral and then that using that and solving for b.
No.
No.
No. Let me quit these things, and then I will explain it to you. Okay. I need to. Okay.